Lavinia and Daniel, first of all, thanks a lot for the kind introduction today. And also I want to thank you all, Lavinia, Daniel, and all the organizers of this conference for actually doing this job, because it's a lot more than picking such a nice location that we have here in Rodders. There's a lot in the background, so thank you for organizing this. I would say that's in the name of all participants. Now, I'm happy to introduce you to my research here. The title is Introducing Scalable Modular Framework to Transfer Point Clouds into Semantically Rich Building Information Models. First of all, I want to just very briefly introduce you to the project that this work was funded from, which is called HumanTech. We have several aims in this project. One is to acquire dynamic digital twin representations of buildings and also of sites in a fully automated manner. It's about also about robotics and wearable solutions in construction. The objective of this, or the aim of this project, is to increase productivity, safety, and well-being in construction industry, but also make construction industry greener and more resource efficient. So why is it important for construction industry to become greener? If you consider this graph here, you can see the global cement production and the global growth of the gross domestic product. Now, if we take the gross domestic product as a measurement for prosperity and for prosperity in the world, you can see that the global cement production is pretty much aligned to the increase in prosperity. This is a problem because construction industry is responsible for 10% of global CO2 emissions, and 8% of these 10% are actually caused by cement production. So this results in 3.6 gigatons of CO2 in construction industry by 2019. So at least in Germany, we think about being climate neutral by 2045, so we have to do something about this. And from a point of a civil engineer in construction, there's basically three options you can choose. One is to reuse existing structures, like if you have an office building but you need more residential buildings in that area, you can pick the office building, do a deep renovation, increase energy efficiency, and then use it as a residential building, for instance. Second option would be to take components of existing buildings and building new structures with these. That's something we also work on in concrete construction. And the third option obviously is to recycle material. That is a pretty common practice yet. In trying to assess what is the best option, obviously reuse will save the most CO2 emissions. Then there's rebuild and recycling, and every disposal of construction material from demolition obviously is a bad thing in terms of resource efficiency and also climate protection. To allow for these three processes or workflows or options, it is important to have data and information about existing structures. So if you think about reusing an existing building, it's good to know what floor area is in this building, what heights, what elements, to assess what else can be done in this building. Then for reusing components from the building, it's important to know what components are in the building for reuse, and also for that's the same case for materials and for recycling. So having a BIM of an existing structure is the essential basis for circular approaches in construction, in the end also to reduce CO2 emissions in construction. If we're talking about scan to BIM, the very first process, the very first step always is data acquisition. Now you guys will probably be familiar with the things I put on the left side of this slide, like drone data acquisition with drones, where you can use LiDAR sensors or photogrammetric workflows. Obviously there are the terrestrial LiDAR scanners, the very pretty basic ones, and then there is a lot of attempts to automate data acquisition, for example by robots, by unmanned ground vehicles, or even by UAVs as well. And there is a lot of technology that tries to fuse several sensors and making combined, for instance, mobile mapping systems. Generally, from data acquisition, you get raw data. If it's photos, you have to reconstruct 3D geometry. If it's point clouds, you need to register them. You need to align them in the same coordinate space. And then you get a clean point cloud from that. It's important to state here that our work completely relies on 3D point clouds. So there's no data, no working with 2D or with image data and steps in between. So we always have something like XYZ, RGB, and maybe some other values depending on the acquisition procedure. Yeah, now I just want to give you a very brief overview on the state of the art. Obviously, time is limited today. Research gaps have been identified by Tang et al. 2010, which is adaptivity to other environments, robustness towards occlusions, and the modeling of complex non-planar structures. Just maybe to give you an idea what's the state of the art in this field at the moment, we have 3 papers here, and basically all these 3 approaches have in common that they tried to exploit the topology of a building. So what's the topology? It's basically the layout of rooms and physical objects in the building. One attempt that was made is like to detect rooms, and then assuming that a room must be delimited or surrounded by building elements, then detecting, for instance, walls and ceilings, maybe even windows and doors, like as surrounding objects of the room. Our approach is different to that, because from the clean point cloud, the first thing we do is performing semantic segmentation on the data. So semantic segmentation essentially means assigning a building object category to every point. Then after semantic segmentation, there are different steps of geometric feature extraction. And in the end, obviously, all information extracted needs to be put together into a BIM model. So first of all, some remarks to semantic segmentation. It's essentially the step from the top left to the right image. Like, essentially, the aim is to find building components in the data. Like here we have a visualization from colors because integer labels that you would normally use aren't, you can't look at these. For semantic segmentations, we experimented with with convolutional neural networks, actually with unit architectures that are quite promising to do this job, but if you're a bit familiar with machine learning approaches, most of these are developed for 2D data, so for dense grids. Now with 3D data, with point clouds, we have sparse data, we have sparse grids, which makes generally these approaches less efficient in terms of computation time. The other thing you have to deal with is training data. So obviously, in the process of acquiring training data, one has to manually annotate point clouds. As there are no data sets available for like structural elements of the buildings that we were interested in this work, you have basically the option of manually annotating data or to acquire synthetic training data. And that's what we actually did here. The first thing you have to think about is how to get buildings, actually, digital buildings. So that's what we did in the first step here. We developed a method to get buildings or to get BIMs that slightly differ in terms of configuration, in terms of number of elements, in terms of length, width, etc. Then using sensor simulation toolkits, you can acquire pretty realistic data like you would, for instance, have from a terrestrial LiDAR scanner, and then you put this data into a training pipeline and get your segmentation model. Yeah, the advantage of this approach, of course, is that you can use the semantic information from the BIM as a source for annotations. So you basically inherit the object class from the BIM object, and then get something like you see in the lower section of the slide, like you get a textured point cloud, and you get a annotated point cloud. An interesting aspect about synthetic training data generation is, at least if you want to automate this process, it is how to actually find locations for your sensor. So in drone acquisition, where Thomas is going to have a talk about later on, and there are probably some more, it's the question of how to get the flight path for the vehicle, and for terrestrial sensors, it's actually how to assess which position is best to acquire a certain object or to acquire a certain group of objects. So that's work in progress. Actually, we have done some attempts on this yet, but yeah, there is a lot of work if you consider also if you consider the features that you will find in actual buildings, and to transfer these into a parameter space and actually get realistic training data. Then after semantic segmentation, the next step seems fairly trivial, but it's a pretty good advance in automating the ScaleBIM workflow, which is filtering according to element classes. So you can take the point cloud and then have every points that were assigned a class like wall or ceiling or whatever. Then the next challenge is to assess what points form a single object. If you look around you, you will encounter that in buildings a lot of surfaces are actually planar, and a lot of surfaces are also horizontal or vertical. So that's an assumption that you can use, and then, for example, for walls, we use Ransack plane fitting, so fitting planes into the data, and then by assessing planes that are oriented the same way, so that are parallel to each other, and that are below a certain distance threshold, then you can actually assume that these form one object. For other objects, like if you think of columns or windows or doors, density-based clustering approaches have proven to be pretty reliable, actually, to group single objects together. Then, obviously, there is a bit in between. I can't introduce you to everything today, but one interesting thing is how to distinguish round and square elements. Like if you think of columns, sometimes they're round, sometimes they're square. Actually, this can be achieved by looking into the point normals. Point normals can be calculated also afterwards in the post-processing, so it's not, it doesn't rely on data acquisition actually. And here, if you consider the normals and the normal change rate for a round object, the normals would slightly change. If you, like, for instance, go around a column, the normal direction would slightly change, whereas for a square object, the normals would only change around the corner. So that's an information that you can use, by doing some statistics, you can then distinguish round and square elements. Then, after grouping, for instance, a wall, as you can see here, the next step is to actually get the dimension, the position, the orientation, and the translation of the object. A good place to start here is determining the oriented bounding box of the object. However, with conventional implementations, we have faced some issues, as you can see here, because the known implementations of the oriented bounding box algorithms, they work pretty good on very heterogeneous shaped point clouds, like chunks of points, but they don't actually work very good on like these square cuboid-ish objects that we face here, or that we encounter in buildings a lot. So we have developed our own methodology to assess the oriented bounding box of a point cloud. Actually here, as you can assume that in many cases the lower and upper bounding of such a wall would be horizontal, you can introduce the problem of bounding box estimation here to a 2D problem. So we project all points onto the XY plane, then determining the convex hull of the 2D points, and then by assessing the volume of every option, where you find the minimum volume, actually you have the minimum bounding box. And yeah, as you can see here, at least for the data we've tested so far, this works pretty good. And from the bounding box, you can then get the information you need for later BIM modeling, like base axis or base points, minimum and maximum set coordinates, etc. Again, for other objects like columns or like round columns that we have distinguished from the square ones in the steps before, a good method to start is Ransack cylinder fitting, so fitting geometric primitives into the data. At least, here you can see a plot of 2 cylinders fitted into the data, these algorithms are pretty robust towards occlusions. So if you have an object like a column that is not scanned from every side round, which is the case very often, even then these algorithms work pretty well and give you pretty nice fitted cylinders. Then if you have achieved all the geometric feature extraction and segmentation steps, it's down to putting all the information together into an open BIM model. Essentially, to do this, we have had good experience with the IFC OpenShell, which is a pretty powerful toolkit. Some of you will be familiar with, I'm sure, for dealing with BIM or with IFC data. Actually, it's also closely interacting with open cascade technologies. So you have, for more advanced geometric modeling, you have like more in the backhand for actually more complex tasks. But obviously, if you think of user requirements and construction practice, you might know that in construction companies, it's more common to work with proprietary data formats. So you have to think about some way how to be sort of platform agnostic, even if for our research working with the IFC OpenShell was pretty good and I think the right approach to choose. So for now, we do an intermediate step here, taking all the information, putting it together into an XML-ish file. You can see here on the bottom left. Actually, it is structured like the building would be, and then taking all the information. But essentially, for later work, you can use such an XML representation to also bring it to proprietary data formats. Now, after we've completed this pipeline here, let's quickly conclude the work. Obviously, semantic segmentation is still a huge issue, even if we have did some successful attempts on this. Actually, if we work with synthetic training data, the problem is, would the segmentation model then work on natural data from data acquisition? Because you have clutter, you have occlusions, you have maybe slight errors from acquisition, etc. For that matter, we are discussing 2 approaches at the moment. One is transfer learning, so training your model with synthetic training data and then taking the last few layers of the model and retrain them with with real-world data that was annotated before. The advantage would be that you need less training data that was manually annotated. The other idea would be to do a refinement using generative adversarial networks. There has been some work on knowledge-based approaches to semantic segmentations that are very promising, because again, if you look around you, you can determine some rules that distinguish like a slab from a wall, like verticality or horizontality, etc. Now for geometric feature extraction, we have observed that our approaches is pretty robust, but we need to do testing and exception handling, obviously, because features in natural buildings, there are a lot different features. And in terms of BIM modeling, it's all down to the requirements of the customer that we have to have a closer look at. And also, we have to think about the IFC format and thinking about maybe extending it, because IFC was not meant to work with as-built data. It's actually for design data. So we have to look for ways how to integrate like deviations of objects into the IFC standard. So now, I want to thank you for your attention, and yeah, I'm happy to ask you a question if there are any.